Wood Science and Technology, Nanoscale Ion Regulation in Wood-Based Structures and Their Device Applications. Chapter 1, Introduction to Nanoscale Ion Regulation in Wood-Based Structures and Their Device Applications. Importance of ion transport, crucial in biological systems such as plants, animals, humans, and various devices. Ionic nanofluidics, transistors, thermoelectrics, batteries, etc. Roles in devices, extends to applications like salt gradient power generators, solar desalination membranes, water filters, ionotronics, sensors, and biological devices. Factors influencing applications. Ion transport mobility and selectivity are key factors, modifiable by adjusting material and device structures. Critical role of pore channel size. Structural engineering of pore or channel size is vital, especially when transitioning from macro-microscale to nanoscale. Nanoscale ion transport. Regulating ion transport at the nanoscale is a powerful strategy for designing high-performance water and energy devices. Materials for ion regulation. Diverse materials and structures used, including carbonaceous materials, CNTs, graphene, polymeric materials, carbon nitride polymeric porous particles, ceramics, boron nitride, silica, clay, and hybrid materials, cellulose graphite, polymer geocomposites. Progress through structural engineering. Significant progress achieved in regulating ion transport behavior via rational structural engineering of materials. Examples of achievements. Examples include achieving high ion conductivity with 2D boron nitride at low sodium chloride concentrations and developing ion-selective membranes using wholly graphene layers for nanofiltration. Novel functionality. By constraining ion movement pathways, researchers achieve novel functionality with further potential to be explored. Specific achievements. Mentioned achievements include high ion conductivity with 2D boron nitride and development of an ion-selective membrane for clean water production. Challenges of existing ion regulation materials and structures. Difficult to manufacture large-size materials with massive nanoscale channels at a low price. Most materials are petroleum-based and non-renewable. Some petroleum-based materials are not biodegradable, leading to plastic pollution. Difficult to meet the high mechanical strength and flexibility requirements for some applications. Stability is always a challenge for practical use, especially for long-term operation. Wood-based materials as promising alternatives, abundant and renewable, possess a hierarchically porous structure composed of numerous hollow cells with pronounced anisotropy, can be engineered to produce high ionic conductivities and high mechanical strength even in the wet state, can be processed at large scale and are mechanically flexible and sustainable. Recent progress on ion regulation in wood-based structures. Modification strategies to tune the pore structure and surface properties of wood-based structures. Ion transport behavior and regulation strategies of wood-based structures in various devices, with a focus on their structure-property performance relationship. Future research and commercialization opportunities. Developing scalable and cost-effective manufacturing methods for wood-based ion regulation materials and structures. Improving the long-term stability of wood-based ion regulation materials and structures. Exploring new applications for wood-based ion regulation materials and structures. Challenges in ion transport materials. Difficulty in manufacturing large-sized materials with massive nanoscale channels at a low cost. Many materials used are petroleum-based and non-renewable, posing sustainability issues. Some petroleum-based materials contribute to severe plastic pollution due to slow degradation. Materials like ceramics and mesoporous carbon struggle to meet requirements for high mechanical strength and flexibility, crucial for applications like portable electronics. Advantages of bio-based materials, specifically wood. Wood, a renewable and abundant bio-based material, is considered an attractive alternative. Wood's hierarchical porous structure evolved over millions of years, offers multi-scale-oriented channels for water, nutrient, and ion transport. Structural engineering from macroscale to nanoscale can regulate ion transport in wood for various applications. Goals and benefits of wood-based structures. Goal to promote fast and/or selective ion transport in wood to achieve high ionic conductivities. Wood's hierarchical fibrous structure provides high mechanical strength, even in a wet state. Facile processing at a large scale. Mechanical flexibility and sustainability make wood-based structures promising for ion regulation and emerging applications. Applications of wood-based structures in ion regulation. Recent progress discussed in ion regulation in wood-based structures for diverse applications. Batteries, supercapacitors, thermoelectrics, etc. Exploration of hierarchical cellular structure. Modification strategies and fundamental ion transport behavior in solution-based porous media. Key influential factors and regulation strategies for ion transport behavior in wood-based structures, including tuning pore structure and surface properties. Structure-property performance relationship. Discussion on the ion transport behavior and regulation strategies of wood-based structures in various devices with a focus on the structure-property performance relationship. Challenges and future opportunities. Overview of challenges and future research and commercialization opportunities in the field of wood-based structures for ion regulation. Chapter 2. Materials, fabrications, and structures. Wood is a ubiquitous material, meaning that is present and found everywhere, and that it has been widely used in various applications due to its well-evolved hierarchical cellular lignocellulosic structure. Recently, there has been a growing interest in understanding the multi-scale mass transport, particularly ion transport behaviors in wood-based structures. The investigation of ion transport behaviors in wood-based structures has opened up a new field of research with promising opportunities. Before delving into ion transport behaviors, regulation, and applications, it is essential to grasp the intrinsic structure and composition of wood, as well as the fabrication strategies and structural tunability of wood-based structures. Chapter 2.1. Intrinsic structure and compositions of wood. Wood is a natural composite composed of numerous cells oriented along the longitudinal direction. The lignocellulosic cell wall is made of cellulose microfibril bundles, makes up 40-50 weight %, hemicellulose 10-30 weight %, and lignin 20-30 weight %. The lumen, that is the void space at the center of the cell of cells along with pits traversing the cell walls, constitute the 3D transport network in wood. The secondary cell wall is composed of 3 layers, namely S1, S2, and S3, with different assembly of microfibrils in each layer. The cellulose microfibril bundle can be further divided into microfibrils, 900 nanometer in diameter, and elementary fibrils, between 1.5 to 3.5 nanometer in diameter. The cellulose microfibril is embedded in the polymer matrix of hemicellulose and lignin and contains both crystalline and amorphous regions along the longitudinal direction. Wood demonstrates large diversity among all wood species in terms of cell types, pore structures, densities, and appearance. The hierarchical pores and announced anisotropy of wood structures are favorable for efficient multiscale mass, especially ion transport and regulation. The anisotropic fibrous cells, cellulose fibrils inside the cell walls, and the linear molecular chains of these fibrils form a unique anisotropic, hierarchically porous material scaffold, enabling directional multiscale mass transport within wood-based structures. Top-down and bottom-up wood-based structures. 2 approaches to fabricate wood-based materials: top-down and bottom-up. Top-down process preserves the hierarchical cellular microstructure of raw wood. Bottom-up process starts with fibrillated cellulose building blocks, forming structures without the wood's hierarchical cellular microstructure. Examples of top-down and bottom-up structures. Delignified wood is a representative top-down structure, obtained via delignification process, preserving hierarchical cellular structure. Cellulose film is a typical bottom-up structure, fabricated from fibrillated cellulose dispersion without the hierarchical cellular wood structure. Structure tunability of wood-based materials. The word tunability refers to the capability of wood-based materials to be adjusted or modified in various aspects. Wood-based materials, both top-down and bottom-up, exhibit diverse tunability. Complex hierarchy of wood microstructure and versatile chemistry of wood components enable tunability. Modification strategies include physical, chemical, or combined processes for tunability. Pore structure and surface properties tuning. Pore structure, for example, size, porosity, tortuosity, can be tuned for ion and fluid transport by processes like delignification, densification, stretching, or hole pouching. Surface properties, for example, zeta potential, wettability. Functional groups are tunable through surface functionalization, delignification, patterning, or coating. Fibril dimension and composition tuning. Fibril dimension, specifically length, diameter, and composition of wood-based structures, can be tuned for diverse properties. Molecular scale tunability. Precise tunability at the molecular scale is achievable. Modifying phase structure, for example, cellulose 1 to cellulose 2, and crystallinity for nanoscale and molecular scale regulation of ion transport. Delignification as a powerful tuning method. Delignification is a popular and powerful method for tuning top-down wood-based structures. Various chemical processes: enzymatic, acid, alkaline, organic, ionic, liquid, photocatalyst, used in delignification. Delignification modifies functional groups or bonds in lignin, decomposing macromolecules for improved hydrophilicity. Effective alkaline solution-based delignification. Alkaline solution-based delignification involves attacking phenolic structures in lignin. Process results in the cleavage of B-aryl ether bonds, generating small molecular fragments. Delignified wood structure retains hierarchical cellular microstructure, enhanced light scattering, and massive nanochannels. Macroscopic changes after delignification. Color of natural wood changes from brownish to whitish after delignification. Microstructure changes include the separation of cells and cellulose nanofibrils, introducing massive nanochannels. Preserved hierarchically porous structure with announced anisotropy makes delignified wood interesting for mass transport and regulation in various applications. Chapter 2-3. Strategies toward improved water stability. Water stability is critical for ion regulation and related applications, as the materials are commonly used in aqueous electrolyte. Natural wood in living tree shows good water stability, but this stability generally decreases after most lignin and hemicellulose are removed from the wood structure. Many strategies have been developed to improve the water stability of wood-based structures, including coating such as bulk coating, lumen coating, and fiber coating, hybridization with other components such as carbonaceous materials, polymers, minerals, and metals, acetylation treatment, counter-ion exchange, cross-linking treatment, esterification, furfurilation. Some specific examples of these strategies are hybridizing lignin particles with cellulose paper to form a uniform coating that binds the cellulose microfibrils together and prevents water from penetrating to the core, acetylation of wood-based structures to convert the free hydroxyls into acetyl groups, which improves stability and anti-fouling properties, counter-ion exchange from Na+ to Ca2+ or L3+ and 2266 tetramethylpapelidine 1-oxyl radical tempo treated cellulose film to improve water stability and oxygen barrier properties. Cross-linking treatment of delignified wood using polyvinyl alcohol gel to improve water stability and mechanical strength. Chapter 3. Ion transport behaviors, properties, and engineering design strategies. Chapter 3.1. Fundamental understanding of ion transport behaviors. When a solid object is immersed in an electrolyte, an electrical double layer abbreviated as EDL forms, consisting of a stern layer next to the solid surface and a mobile layer extending to the liquid. The characteristic screening length of the electrical double layer EDL, called the Debye length represented as LD, can be determined or calculated by the equation. Within the electrical double layer EDL, the potential decreases exponentially from the interface to the center of the channel. The surface charge is balanced by the accumulation of counter-ions and the depletion of co-ions. In microchannels or high-concentration electrolyte solutions where the Debye length is much smaller than the characteristic dimension h of the microchannel, channel size, the ion transport features bulk behavior. Either channel size decreases to nanoscale, either or the concentration of the electrolyte solution is low. Debye length is comparable to or larger than the characteristic dimension h of the channel. In this case, the ion concentration inside the nanoscale channel is governed by surface charge, and the ion transport behavior is significantly different from bulk behavior. The ion transport inside nanochannels shows a typical nanofluidic effect, that is, the ionic conductance becomes almost constant regardless of the ion concentration of the bulk electrolyte solution. This nanofluidic ion transport behavior has been regarded as one of the most powerful principles in ionic and fluidic fields and widely explored in various ion-regulating devices. Chapter 3.2. Regulation of ion transport in wood-based structures. The ion transport behavior in wood-based structures can be regulated by tuning the surface properties, mainly the surface charge density or zeta potential, channel size, or a combination of both. Wood-based structures offer large numbers of multi-scale channels for ion transport. The ion transport behavior can be tuned by modifying the dimension and morphology, e.g. porosity, pore size, and alignment of fibrils, the surface properties, e.g. functional groups, wettability, and surface charge, and/or the molecular structure, e.g. ion intercalation exchange, transformation from cellulose I to cellulose II, of wood-based materials. Chapter 3.21. Tuning surface charge properties. The surface charge density of a porous medium in electrolyte solution can be affected by the surface functional groups, defects of the crystalline structure, and pH value of the electrolyte. The zeta potential is an indicator for the surface potential of the solid interface and can be measured experimentally. The zeta potential of wood-based materials can be tuned by surface functionalization, such as grafting cationic functional groups or oxidation treatment. Chapter 3.22. Tuning channel size. Channel size plays a decisive role in the ion transport behavior of a solid electrolyte system. By tuning the channel size, especially reducing the channel size from microscale to nanoscale, the surface charge density and electrical potential distribution within the channel vary dramatically. Thus, the ion transport behavior can be substantially regulated from bulk behavior to nano behavior. The channel size of wood-based structures can be tuned via diverse strategies, such as delignification, densification, stretching, swelling, hybridization, and so on. The channel size can also be estimated by fitting the conductivity trend at various concentrations. Overall, the key points of this section are that the ion transport behavior in wood-based structures can be regulated by tuning the surface properties, channel size, or a combination of both. Tuning the surface properties and channel size can be achieved through the integration of physical and chemical structural modification. Thanks for watching.